Good day. Today we are learning about UV visible spectroscopy, Module 2. You will gain knowledge about Lamberts law, its derivation and deviations. Let us learn about laws governing absorption of radiation or Lamberts law. The two laws related to the absorption of radiation are: one is Beer's law, which is related to concentration of absorbing species. Second one is Lambert's law, related to thickness or path length of absorbing species. These two laws are applicable when intensity of incident light is equal to intensity of absorbed light plus intensity of transmitted light. No reflection or scattering of light takes place. What is Beer's law? Beer's law states that intensity of a beam of monochromatic light decreases exponentially with increase in the concentration of absorbing species arithmetically. Accordingly, the decrease in the intensity of incident light with concentration is proportional to the intensity of incident light. That is, minus di by dc is directly proportional to I. Removing and introducing the constant of proportionality k, you will get minus di by dc is equal to ki. K is the proportionality constant. Upon rearranging the terms, you will get minus di by I is equal to kdc. Upon integration I is equal to kc plus b, where b is constant for integration. When concentration is 0 and there will be no absorbance, then I becomes I naught. Then we can write the equation 1 as integration I naught is equal to b. Substituting the value of b in equation 1, we will get integration I is equal to kc minus integration I naught. Then taking I naught into left hand side, you will get integration I naught minus integration I is equal to kc. And this is like log a minus log b, which is equal to log a by b. Then we can write integration I naught by I is equal to kc. Removing natural logarithm, and we can write integration I naught by I is equal to e to the power of kc. Reversing the terms, we will get I by I naught is equal to e to the power of minus kc. Then I is equal to I naught into e to the power of minus kc. This is called Beer's law. Let us learn about Lambert's law. What is Lambert's law? Lambert's law states that the rate of decrease of intensity with the thickness of the medium is directly proportional to the intensity of incident light. Then we can write minus di by dt is directly proportional to the I. And like Beer's law, when we derive this equation, then we will get I is equal to I naught into e to the power of minus kt. Equations 2 and 3, when we combine these two equations, we will get I is equal to I naught into e to the power of minus kct. And converting natural logarithm to base 10, and we will get I is equal to I naught into 10 to the power of minus kct. Then we can write this as I by I naught is equal to 10 to the power of minus kct. I naught by I is equal to, reversing the terms here, I naught by I is equal to 10 to the power of minus kct. And taking log on both sides, you will get equation 4, that is log I naught by I is equal to kct. It can be learned that transmittance T is equal to I by I naught and absorbance A is equal to log I by T. Hence, the absorbance we can write as A is equal to log 1 by I naught. And finally, we can get absorbance is equal to log I naught by I. And here, using these equations 4 and 5, we will get A is equal to kct. Or we can write A is equal to ECT, and this is the Beer-Lamberts equation, where A is the amount of light that is absorbed for a particular wavelength by the sample. K is molar or molecular extinction coefficient. T is the path length. C is the absorbing species, where E can also be expressed as E is equal to E 1% 1 centimeter into molecular weight divided by 10. E 1% 1 centimeter at a wavelength is constant value for each drug, and it can be seen in pharmacopoeias or standard books on the subject. This value is useful in determining the concentration of drugs in sample formulations or in solutions. Let us learn about deviations from Beer-Lambert's law. A system is said to obey Beer's law when a plot of absorbance versus concentration at a particular wavelength is drawn, a straight line passing through the origin is obtained. You can observe the graph here. Absorbance versus concentration and a straight line that is passing through the origin. The straight line is obtained by using line of best fit or method of least squares, or by joining the maximum number of points in such a way that positive and negative errors are balanced or minimized. When the straight line is not obtained, a non-linear curve is obtained. Now the system is said to undergo deviation from Beer's law. Such deviations can be positive deviation or negative deviation. What do you mean by positive deviation? Positive deviation results when there is a small change in concentration and produces a greater change in absorbance. And negative deviation results when there is a large change in concentration and produces a smaller change in absorbance. Apart from these two deviations, that is positive and negative deviations, there are other deviations from Beer's law also occur due to following factors. The deviations from the Beer's law may be due to interaction of solute molecules with each other or with the solvent, or may be due to instrumental factors. Let us read one by one. First one is instrumental factors. Instrumental factors like polychromatic radiations, stray light, mismatched cells, improper slit width, fluctuations in a single beam. All this causes deviations from Beer's law. Due to polychromatic radiation. Polychromatic deviations occur when more than one wavelength of light is present and the radiant power of these wavelengths is absorbed in different proportions by the unlight. The difference between the molar absorptivities of the compound at different wavelengths causes deviations from Beer's law. Hence, the Beer-Lambert's law is strictly followed when a monochromatic radiation exists. That means we should use monochromatic radiation to obtain Beer-Lambert's law. Next one, due to presence of stray light, also deviations from Beer's law occur. Light scattering inside the detection area of the spectrophotometer causes stray light deviations from Beer's law. The resulting absorbance deviation increases with increasing the absorbance because the stray light represents an increasingly significant part of the signal that reaches the detector. Such instrumental deviations from Beer's law always cause underestimates of the analyte. You can observe in the diagram the internal stray radiation along with sample absorbance also falls on the detector. Thus, deviations from Beer's law occurs. Due to mismatched cells or cuvettes. Cuvettes are used to hold the sample solution. If the cells holding the analyte and blank solutions are having different path lengths or unequal optical characteristics, it is obvious that there would be a deviation from Beer's law is observed. In today's instruments, this problem is generally not observed because the optically matched pair of measuring cells are using in the laboratory. However, if it is present, appropriate linear regression to quantify this deviation must be made. You can observe the different cells of different path lengths and different optical characteristics. If we use such different optical characteristics for both sample and the blank, deviations from Beer's law occur. Next one is physico-chemical changes in solution. Factors like association, dissociation, ionization, incomplete reaction, refractive index at high concentration causes deviations from base law. Let us learn one by one. Ionization or change in pH. For example, if you take phenol red when it is transformation when moving from acidic yellow to basic form, that is red color. Due to this resonance, the electron distribution of the bonds of molecule changes with the pH of the solvent in which it is dissolved. Since UV spectroscopy is an electron-related phenomenon, the absorption spectrum of the sample changes with the change in pH of the solvent. When this absorbance is not noticed, then we can observe deviations from base law. You can see here the transformation of phenol red from yellow to red. So here, if we are not observing this transformation, that is acidic form which is yellow in color and basic form which is red in color, definitely the deviations from base law occur. Second one, dissociation. Aqueous solutions of potassium dichromate which changes from yellow to orange on increasing the concentration of hydrogen ions causes due to chromate to dichromate conversion. If we are not observing this change, that is chromate to dichromate conversion, then deviations from base law occur. Next one is association. Complex formation due to association can result in color changes with concentration changes. Then deviations from base law occur. For example, cobalt chloride, which changes color from green to blue due to association. If we are not observing or considering this change, then deviations from base law occur. Next one is incomplete reaction. When sufficient time is not allowed for making absorbance measurement, or when the readings has made when the color has faded away or due to instability of the color, deviations can occur. So when we are doing experiment, we should allow the time for color development. For example, you can see here determination of iron using thioglycolic acid before completion of reaction. If you observe this sample before completion of reaction, you will observe deviations from base law. Next one is high analyte concentrations. These are also possibly alter refractive index of the solution, which in turn could affect the absorbance value, hence deviations occur. Apart from instrumental deviations and physicochemical deviations, there are other deviations also occur in the sample solution. Deviations may also occur due to presence of impurities that fluorescence are absorbed at the absorption wavelength. Deviations may also occur if the solution species undergo polymerization. Beads cannot be applicable to suspensions or emulsions in UV region. Real deviations. These are the fundamental deviations due to limitations of law itself. Presence of some other substance that absorb at the same wavelength as the solute may also cause deviation. Environmental errors such as solvent, temperature and pressure may also cause deviations. These are the deviations from the Beer's law. Today you have gained knowledge about Beer-Lamberts law, its derivation and deviations. There are important terms in UV-visible spectroscopy. Let us learn about some terms. Chromophore. Chromophore is a group of atoms responsible for UV-visible absorption of the molecule. For example, double bonds, aromatic rings, ethylene, acetylene, carbonyls, acids, esters and nitrile groups. These chromophores are covalently unsaturated. Oxochrome. An oxochrome is a functional group of atoms with one or more lone pairs of electrons. When attached to a chromophore, alters both the wavelength and intensity of absorption. Hence, oxochrome is a substituent that increases absorption of molecule. Example, OH, OR, NH2, NHR, etc. Isobestic point. Isobestic point is the wavelength in which the absorbance of two or more species are the same. You can hear this is the isobestic point of the sample. Bathochromic shift. A shift of lambda max to lower energy or longer wavelength is called bathochromic shift. It is often called as redshift. It can occur due to increase in conjugation, addition of alkyl substituents in a molecule. Hypsochromic shift. A shift of lambda max to high energy or shorter wavelengths is called hypsochromic shift, often called a blue shift. It can occur due to removal of double or triple bonds by saturation dealkylation. Hyperchromic effect. An increase in the molar absorptivity or intensity of absorption. Hypochromic effect. A decrease in the molar absorptivity or intensity of absorption. Chromogenic agent. Chromogenic agents are those which is capable of forming a chromophore or color by complexation, chemical reaction, ionization. For example, ferric chloride. When ferric chloride is added to salicylic acid produces a violet color with lambda max at 530 nanometers. So, ferric chloride is called as chromogen. These are some important terms in UV visible spectroscopy.